I'm going to get rid of this and ask you to think about these things, this particular problem, in terms of a wave chart. So we're going to have more than one wave. So wave 1, wave 2. And what's important about the waves? Well, if you want to know whether it's constructive or destructive, then you look at the difference between the two phases. And so we're going to put one wave and look at the pieces of total phase. So there's one of the pieces. There's 3 pieces to the total phase. There's one of them. There's another. And there's the 3rd piece to the total phase. If I add all those pieces to the total phase, all these 3 pieces, I get the total phase. And what's important is the difference between the 2 phases. This is delta phi, phi 2 minus phi 1, say. You can subtract it either way, but I'm going to subtract wave 1 from wave 2. You could go the other way. It doesn't really matter. So let's look at this problem. Radio station transmits at about 1,070 kilohertz. So that's about just over 1,000,000 hertz. 1,000,000 cycles every second. That's a radio frequency. From 2 towers spaced 140 meters apart, located to the north of Rosser Hall by 1,400 meters and 1,540 meters. So that's what this picture is meant to be. Here's Rosser Hall. Here's where we're standing. North of us is that way. 1,400 meters that way. Let's say we have a radio station that's broadcasting a signal. Let's think of it as a sine wave right now. Radio stations broadcast lots more complicated signals, but let's just have them broadcasting a sine wave. It says the frequency, so it really is just one frequency, so it really is a sine wave. 1,070 kilohertz. Another 140 meters that way. So the first one is broadcasting. Well, it broadcasts its wave in all directions, but one of those directions is straight toward Rosser Hall. 140 meters farther, another one broadcasting in all directions. So it's broadcasting toward Rosser Hall also. Both those waves reach Rosser Hall. And so the result of that, each one emits a radio wave in the direction of Rosser Hall. As a result, the transmission at the entrance to, as a result of this transmission, the entrance to Rosser Hall receives a transmission of constant maximum amplitude. So maximal amplitude. So what does that mean? Constructive or destructive? Constructive interference. That sentence right there tells you, think about constructive interference between those 2 sources. You get a signal from each of them, and they interfere constructively. So what should delta phi be? Two pi times an integer is all I really know. But I know that as soon as it says a constant maximal amplitude, this delta phi is something I know right away. 2 pi times an integer. Let me tell you one other thing that we always use. We only have one clock. All the times that we work on for all these different sources, if it's 2 p.m. here, it's 2 p.m. at each of those towers. So there is only one time. Both towers put out the same frequency. What does that tell you about Okay, let me just write down the difference. 2 pi over t2 times time minus 2 pi over t1 times time. What does that equal? 0. Anyone think it's not 0? Why 0?
Because they're transmitting at the same frequency, so they should have the same period.
Radio station transmits at that frequency from 2 towers, so they're transmitting at the same frequency. So they have the same period. So I don't need to write T1 and T2. I can just write T. Since period, capital T. Because the times are the same, the clocks are the same for the two. If the times are the same and the periods are the same, then there's no phase change here. There's no phase difference. So there isn't a phase difference from that first piece. That is always going to be true if the two sources have the same period. They have the same frequency. That first piece will never give you a phase difference. I will let you deal with the rest of it, talk about it for a little while, see if you can figure it out. I notice here that there's 2 pi over lambda times x, and they don't give you lambda, they give you frequency. Suppose I told you the speed of light, could you get lambda? What would lambda be?
Well, it would be the same for both of them.
It would be the same for both, that's true. Suppose you know the speed and the frequency. How are the speed related to, this will be on the quiz, so I'm not even going to finish. I'll tell you. The frequency times the wavelength tells you the speed. I'm going to tell you that the wavelength, of course, this says the wavelength is the speed over the frequency. I'm going to tell you that the speed of light is about 3 times 10 to the 8 meters per second. And this frequency here is 1,000 times 10 to, a little over 1,000 times 10 to the third. So let me say it's 1.07 times 10 to the sixth. Doesn't really look like a 6 to me, so let me try to make it a 6. 1.07 times 10 to the 6. So that tells you the wavelength. You can get the wavelength fairly quickly and use that to figure out the difference in the phases from wave 1 to wave 2 due to the x, and then figure out the difference due to phi. Yeah?
Why do you use the speed of light if people work in the sound?
It's a radio station, actually. So it's transmitting radio waves. And I'll tell you that radio waves are electromagnetic waves. We haven't gotten to that yet, but I'm going to tell you that. So it's not the speed of sound, it's actually the speed of light. All right, so I'm going to give you a few minutes to work on that. And then we'll talk about it. And then we'll go on to one that I think is trickier, more interesting, and a good one for you to think about. Has anyone calculated a wavelength yet? What? 2.8? 280? Is it 2.8 or 280? 280. So wavelength is 280. So what's delta x, the difference between the two distances? 140. And that's how much of a wavelength? Half a wavelength. So if you put in half a wavelength for the difference in that second column, what does that tell you in terms of the phase difference? I hear pi. Do I hear anything else? Yeah, delta x, so what is it really? I mean, I can put it all in. 2 pi over 280. I can factor that out because that's in both terms because the wavelength is the same for both terms. And then it's just x2 minus x1. x2 minus x1 is 140. So if you work that out, you end up with pi. Is pi phase difference going to give you a maximal amplitude? No. So that tells you something about those two. The fixed phase of those two differs by, well, first of all, it's different. It can't, the difference between phi 2 minus phi 1, what's a possible difference for phi 2 minus phi 1? Pi works, 3 pi works, minus pi works. All of those are possible phase differences. That's telling you that those two, let's say it's pi. Let's make it pi. So when one of them is putting out a maximum signal, what's the other one putting out at exactly that same time? A minimum signal. If the fixed phase is different by pi, that just tells you that at the same time, they're doing the opposite things. One's putting out a maximum signal while the other's putting out a minimum signal. The end result of all of that is that there's a maximum at Rossler Hall. In fact, anywhere along here, suppose I wasn't at Rossler Hall, suppose I was halfway. What's the difference in the two x's if I'm halfway here? Still 140. How about if I'm up here, way up here? What's the difference in the two x's? 140, or negative 140, but that negative sign doesn't mean anything. That changes pi to minus pi, so it doesn't matter. Now out here, that's different. Out here, they don't differ by 140 anymore. If I'm over here on the left, if I'm exactly in the middle over here on the left, then there's no difference at all in the distances. And if I get down here, then I'm closer to this one than I am to that one, so there is a difference. And so those distances, the difference in the distances, the delta x's, if I'm over here, the delta x's are going to depend on where I am over here. And so it gets a little more complicated, and that's a problem for next week. I don't want to go over any more of this. I hope we've talked about it enough that you can figure it out on your own, because I wanted you to think about this one. So I wanted to give you a few minutes, 4 or 5 minutes to think about this one, or maybe 6 or 7, and then we'll talk about it. This one is, for various reasons, I like this question. There's a graph here. So there's two waves again. The displacement of the first wave we call y1. It's a function of x1. By the way, whenever I say x, and we have two sources, x equals 0 is always going to be the location of the source. It says it right here. Call this wave 1. The wave 1 has a source at x1 equals 0. This is supposed to say x1, not just x. So all waves are going to start, we'll always start it at its source, which has a kind of sense to it. So x1 equal to 0 is right here. The source of the wave is right there. Wave 1, and so here's a picture of y versus x. So that's a snapshot of wave 1 at t equals 2 o'clock. So at 2 o'clock, somebody took a snapshot of wave 1. It looks like that as a function of how far away you are. Wave 1 and wave 2 are in the same medium. Actually, superposition has to be in the same medium. Two waves are at the same location at the same time. Then they're at the same spot, and that means they're in the same medium. So it's a little bit redundant to say they're in the same medium. Anyway, at a point 10 meters from source of wave 1 and 8 meters from the source of wave 2, the two waves interfere constructively. So at that point, 10 meters here from wave 1, you can see that. 8 meters from wave 2, which they don't show you. If you sat right there, you would see giant oscillations as both waves went through. Really big. How big? Oscillations have an amplitude of 5 meters. So it would go up 5 meters, down to equilibrium, and down 5 meters. So that would be the big oscillations. Plus and minus 5 meters at that point where they meet. In the space below, sketch y2 of x2 versus x2. So the wave 2 has its source at x2 equal to 0. So your job is to sketch the other wave. So think about it, talk about it, draw the picture. First of all, constructive or destructive interference at that point? Constructive, okay. Two peaks come along at the same time, two valleys come along at the same time. Yeah.
Yeah, I was thinking of it as well. Is it
Why is that 5 not 6?
interference or interfering constructively? Like, it doesn't seem like it's perfect constructive interference.
They interfere constructively. Delta phi is equal to 0. I'm telling you delta phi equal to 0. So they absolutely, a peak crosses the peak. They interfere constructively. Now, the first one, sketch, has a peak with a magnitude of 3. What's the second one going to have an amplitude? 2. So that's what you read into this. You try not to assume anything. You try to look at what they have and figure out how to draw the picture. So continue figuring out how to draw the picture. Yeah. So do they have to have the same wavelength? Well, what it says is that the two waves interfere constructively. So delta phi is equal to 0. So if they have different periods, if they have different wavelengths, they have different periods, right? Suppose they had different periods. What is... If they have different periods, look at what happens to this piece of the phase chart. The difference between those two pieces, this will be a number that isn't 0 if they have different periods. If this isn't 0, then the difference in the phase is going to depend on time. That means sometimes the phase, it'll be constructive, sometimes it'll be destructive, later on it'll be constructive again, later on it'll be destructive. If it says delta phi is 0, what it means is delta phi is 0 for all time, and that is telling you that the two periods have to be the same, it turns out.
It means that it's
For the wavelength.
equals to 0 at all points, because the way I'm reading it, it's saying at that point, 10 meters from wave 1 and 8 meters from
At
wave
that
2.
location.
So does that mean because it's delta phi is equal to 0 at that one point?
It doesn't have to be 0 at every other point in the world. It is 0 at that point, and it doesn't say any particular time it's 0. It's 0 always at that point. And if it's 0 always, then it doesn't depend on time. And if the phase difference doesn't depend on t right here, then those two periods better cancel each other. So they have to be the same period, or else suddenly you have interference that depends on time. And we'll talk about interference that depends on time in a week or two. Well, speaking of depending on time, we're almost out of time. So I want you to, so let me tell you why I like this one. The reason I like this one is because if you look out here at 10, it's at the equilibrium point. It's not at a peak, and it's not at a valley. So if it's going to be constructive interference with another wave, what does that other wave have to be at 8? Yeah.
At equilibrium point, but going into a trough, like the same position.
Well, I'll go along with that for a second. At equilibrium is where it has to be. So here's a wave The source is there. If the source is at x1 equals 0, what direction is the wave moving? Right or left? How do waves move compared to the source? Do they all move toward the source? They move away. The wave is moving to the right because the source is at x equal to 0. So this wave is moving to the right. So it's right now at 0. What's it going to have very soon? A peak will show up there very soon. This wave here, its source is at its x2 equal to 0. That means it's also moving to the right. Right now it's 0. Shall I draw the wave this way so that there's a peak up there? Or shall I draw it this way so that there's a peak up there? Which one? First one? Anyone think it's the second one? You want the wavelength to be the same. You want this at 0 or at 8 to be 0. And you want a peak to be showing up pretty soon. So that this peak shows up at 10 at the same time that this peak shows up at 8 and gives you a big result. All right.